Okay, hello everyone. So today we are learning about work, power, and energy. And basically, we are learning about the energy part and also about energy conservation and about efficiency. Okay, so let's move into the first slide. Here you can find it is work. So work we have in daily life, we said that it's like a job or like an occupation, like what you are doing, and you can say I'm doing like something, and we can call this as a work, right? On the IGCSE physics, we said work is a kind of energy or like a dynamic energy. So if we want to make the energy into two parts, we can say here are two kinds. The first is dynamic energy, and the second part is a static energy. So what is for dynamic energy for? Like when you are taking in some food or you're just like cleaning your room, you can find you're just absorbing the energy or just your release energy. So this is kind of a dynamic. We can say that the energy has an input or an output. Okay, here is dynamic means. And for static energy, we can say like energy stored in the food or like in some energy stored in the substance, we can say that is a static energy. So what down, you can say that is a dynamic energy. It is also always like gives out energy or absorb energy. Okay. So like we have just discussed about clean your room, right? So once you clean your room, you can find when you're using your hands and exert a very big force, like to clean your room, and you can just to wash all your floors in the room, right? And if your room is so big, that means that the distance you have to wash all the places is very big. So it's also very hard for you. It's a lot of work for you, right? So now we can using the two like physical quantities to represent for the work. Like one is force, another is the distance. So you can use force times distance means the work. Once you exert more force and once your room is very big, that means to clean up your room means a very big work. Okay, so here force times distance equals to the work. Okay. And remember that force unit is Newton and distance unit is meter, and for works unit is joule. Okay, that is because it is coupled with a very famous physics called joule. Okay, so we're using his capital letter of his name to represent for the unit of the energy. Okay. So please remember that here, like in this figure, like you want to calculate the 1 joule of the work done, like you're putting a force, 1 Newton force on an object and you make it to move 1 meter. So then you can use the formula that the force 1 Newton times the distance 1 meter equals to 1 joule, like this way. Okay, so here is a work done on this substance. Okay, so let's to the next part called power. So efficient power is just like the efficiency we use in our daily life. Like you're cleaning our room, it's the same job, right? Maybe sometimes you are playing TikTok or sometimes you are playing YouTube, but you're not focusing on your work, right? So maybe it will take a long time. We can say that you have a very low efficiency, right? So as time is very long, the efficiency for you or the power for you is very short or very small, right? If your time taking is very short, that means you just worked very focusing and you're just focusing on your job and try to clean your room very quick and very maybe high efficiency. Okay, so because that when time taken is very small, efficiency or power will increases like this way. Okay, and also if you've done a very like hard work in very short time, also you can set your efficiency very high, right? So like also work done increases, well, let the efficiency increases. Also time taken that doesn't change, but the work done decreases. That means you do less work in same time, right? So here we can use these two quantity to represent for the efficiency. So we can set power equals to work done over time taken. If here work done increases, that means the total fraction number will also increase. If the time taken will increase, that means the total fraction number will decreases like this way. Okay. So here is power's meaning. Power equals to work done over time taken. So here is power. Okay. And remember that power's unit is like watt. We're using the first letter is W. Okay. Like here. So you can find that some you are using your iPhone, you're using your iPad, you're using your MacBook. Maybe it also has a like a charging efficiency or like a charging power, right? You will say that, oh, maybe if we design this, if you want to charge your iPhone, it has to become like a 60 watt or like 70 watt. Like it's a very correct number. That is because the power is the same. Okay, so here is power. Okay, so let's move into the next part that is called energy. And we have talked about that work is a kind of dynamic energy. And for the energy, we can say right here is a like a static energy, just stored in the object. Okay, so here we are first moving to the kinetic energy. So imagine you're on the road, maybe a very high speed road, and it has a truck, right? So you can say that truck has a very big energy, or it contains many energy. Okay, so we can find the mass and the velocity of the truck determine the energy for this, right? So different from the momentum we have learned before, that momentum formula is momentum equals to mass times velocity. But to remind that here we want to make a difference with the momentum, so we let the energy equals to a half times mass times velocity square to make a difference with momentum. Okay, like this way. Okay, so here is for kinetic energy. Okay. So like you can see in this figure, the girl is playing the like a swing, and if you want to determine where she has a like a most kinetic energy, so you can determine that, oh, maybe mass doesn't change, right? Because for a person, mass is a constant number and velocity changes every time. So you can find here when she is at the bottom places, you can find that she's just going to swing, right? So if she wants to swing up, it has a maybe very big velocity. But when she swings to the very top, you can find here that it's almost like stay still on the sky, right? So here maybe the velocity approximately equals to zero, right? Like this way. So we can say the mass doesn't change, but the velocity at the bottom is bigger. So we can say here using the formula, kinetic energy equals to half times mass times velocity square. So that when she's at the bottom, she has a higher kinetic energy. Okay, this is how we can use the kinetic energy to make a comparison. Okay, so also to remember that the kinetic energy unit is joule, the same as the work. Okay, okay. And for the next part, we can set energy here in the gravitational potential energy, like PE. Here you can see there is an electric motor. Like here, if you put at the bottom of the mountain, you want to just move on, you have to like you have to give in some energy, like you have to give some electricity, or like you want to boil in the oil, like they want to become the like a kinetic energy for the car, right? And it can make a motion. And once you get to the top, if you want to just boost downward, it's also very easy for you, right? Maybe you can find here, you don't need to, you don't need to using any energy anymore. You just control brake, right? So you can find that on the top of the mountain, the car just moves directly down and very easily without any like resistive force, right? So here, once it slides down, you can find here some velocity. That means it has a kinetic energy, right? So which energy just transfers to kinetic energy? We can just to imagine our head. So here you can find because there's a mountain, right? The mountain means a very big height, and the big height for the car means a very like potential energy stored in the car, right? And once it just moves downward from the mountain, we can say that here it transfers to the kinetic energy and it can move by itself, right? Okay, so here for the potential energy, we can say that the formula is the mass times gravity times height. Okay, once you have a very big weight and once you have a very big height, you can times them together and there's a potential energy. Okay, so here you're using mass times gravity times height to represent for the potential energy. So here's the unit also for joule. Okay, and the total name is joule, like here. Okay, so here is mgh. Okay, and after that, I hope you can do this work, just trying to using the formula we have learned before and try to use the concept we have learned before, okay? So here you can find the figure one shows a helicopter which stationary at a height of 1,500 above the ground, right? And here you can find the question one states the two conditions necessary for helicopter to remain in equilibrium, okay? We just try to solve this problem and just to determine what is the condition for equilibrium. Okay, so let's moving back to this question. And here you can find once you stage two conditions that makes like helicopter to remain in equilibrium. So we have to first determine what is the concept of equilibrium. So in our daily life, we can say that equilibrium means an object that doesn't have any like motions or just is at a very like a balanced place, right? Maybe it has a constant velocity, but it must be in balance, right? So we can just trace back to the Newton's three laws, right? We have learned in the Newton's first law that if there's no forces or the resultant force is zero, that means the object is in equilibrium, like it is at a constant speed or it just stays still, right? So first of all, you can find very easy that resultant force must equal to zero, right? So here we can set the first condition is resultant force must equal to zero, okay? This is condition one. And for condition two, we can set if it want to becomes in equilibrium, that it doesn't have any rotation, right, for the helicopter. Like here, you can find if it is rotates, that means it doesn't mean the equilibrium, right? Because here it also has a motion, right? So here you have to make the resultant motion, sorry, resultant moment. That means the turning effect, right? Also needs to equal to zero. Okay, so here is for this two part. Okay, then maybe you will also have a question. So why we can just think of this? Why you can think the total resultant force and total moment equals to zero? So you can find here there are two propeller for the aircraft or the helicopter, right? So for the propeller, you can find it is at the top, and this makes like a upward motion or downward motion, right? So here is for the top propellers using, right? And for this propeller usage, we can say that because it at the end of the helicopter and it applies a force just towards or just turn left or turning right, right? So this makes it to turn around and gives it like a moving forward force, okay? So you can find using these two parameters, like their usages, you can use them to find here the upper to give the resultant force to zero, and like the right of the propeller, you can find this gives a resultant moment. Okay, moment, right? Okay. Okay, so just moving to the second question, and here you can use in g equals to 10 to solve the problem. Okay, g equals to 10 right here. Okay, so here in the question is that the mass of the helicopter is 3,200 kilogram, and here is the potential energy of the helicopter as it rises to the ground about 1,500 meter, right? So after that, you can use in the formula that the potential energy or the GPE equals to mass times gravity times height, like this way, okay? And for mass, we can say that the helicopter's mass is 3,200 kilogram. And for G, we can say that the G here is 10 Newton per kilogram. And for the height, you can set here it just rises from the ground to 1,500 meter, okay, like this way. And then you can just calculate the GPE and remember that the unit is joule right here, okay? So here is for our total exercises in the energy part, okay? And now let's move to the next part called energy conservation and efficiency, okay? So what is about energy conservation? We have already learned about the momentum conservation, right? So energy conservation is also the same meaning as the momentum conservation. That means total value for energy doesn't change and energy just transfers into different forms, okay? So here you can find in this figure, the child just like throwing up a stone, right? And once he threw up the stone, you can find here using his muscles to give the force to the stone, right? So here stored in his muscles here are chemical energy, right? Chemical energy stored in his like hands, and then he just towed up the stone, right? So once he towed up, the chemical energy in his muscles just transfers into, I guess, the kinetic energy for the stone, right? Because it has a velocity using the formula, kinetic energy equals to half times mass times velocity square. We can calculate that here is a kinetic energy, right? And after it's moving to the highest point, we can say that its velocity just approximately equals to zero, right? Because it just reaches the highest point. And here we can find it has a very big height, right? So it means that it has a very big, like gravitational potential energy, right? Here GP means the mgh, right? And as the stone falls to the ground, you can find here its velocity just increases and increases. You can say that once its height and decreases, it just turns the GPE to the kinetic energy, right? Because here GPE means mgh, and here actually is decreasing, and for the kinetic energy, velocity is increasing. So GPE just transfers into kinetic energy. And as the stone hits the wall, you can find here the stone energy just gives the wall. Okay, like you are using a hammer to hit on the wall. Here must be increases the temperature. Okay, like this way. So this is stone hits a wall, and you find that velocity suddenly changes to zero, and this gives thermal energy to the wall and the stone. Okay. So after that, we learned about energy conservation. That means energy just transfers in different type, right? And we have also to learn about a word called efficiency. And to remember that there's a difference between efficiency. Like we have already talked about the efficiency, like just like power, right? Power's formula is power equals to work done over time taken. And here's the efficiency, just like a productivity, like your factor, like your boss of a factory, and you want to produce a product. Maybe here you are using a hundred tons of like steel to just made about 80 tons of the toy. Okay, like this way, you're a toy factory. Okay, and if you are the boss, maybe you want to increasing the productivity, right? Maybe you are using the 100 tons of steel to maybe produce 95 tons of toy. That will have a higher productivity, okay? Like this way. So we can using the word efficiency to like describe the converting ratio, like here is a like productivity, okay, sorry, productivity, okay? So here you can find, if here we are just boiling the petrol or boiling the diesel, we are using the engine, and only 25 joule, like a kinetic energy for the car, makes the car's motion just 25. So it's such a very small number, right? So it just, we can say, if we just want to calculate the useful work, or like just want to try to calculate the kinetic energy or the total energy, that is just a 25% productivity, right? And that doesn't mean that 100 joule just turns into 25 joule, or it doesn't obey the laws for energy conservation. And here you can find there are many other arrows here, like pointing to the up or pointing to the down, right? And there means like some other kind of energy, like thermal energy once you burn the oil or petrol, like other kinds of energy stored in like the chemical energy or like other energies. Okay, so only 25 joule are like turns into the kinetic energy. Or maybe here you can find thermal is 50 or other is 25, so total is still 100. Okay, so the obeys the laws for like the energy conservation, but we have to determine that this is a type of the transfer that doesn't 100% to transfer to the type of energy we want. So here we can talking about efficiency. Okay. So after your like energy categories increases, like you just varies from the petrol to the diesel to the electric motor, and you can find here in the electric motor, it has a very high efficiency, right? So I remember the problem that in the past papers that it asked that why electric motor can be replaced to the petrol or like the diesel. So you can answer that, oh, maybe it has a very high efficiency, right? This is the first reason. And for second reason, you can also say that, oh, for the electric motor, it is just a very clean like energy, okay? It is very eco-friendly, okay? So here is why we are using the electric motor in this way. Okay, and for the human's body, you can find your body, your energy transfers is also at a very low efficiency. Like if you exert 100 joule of energy in your muscles, maybe you can only transfer 15 joule to the bicycles or just you're running to transfer into your kinetic energy for yourself. Okay, so here the efficiency is 50%. Okay, so here we can using this to determine a formula is efficiency equals to the useful energy output over the total energy output. And here useful energy output means like if you're driving a car, that is just as kinetic energy. If you're dragging a object, it just means like it's like a kinetic energy or like it's a potential energy when you lift it up. Okay, so here is for useful energy. Just we want to use the energy. And for total energy, like we're like burning the petrol, burning the diesel, right? And maybe it can release a lot of heat and a lot of energy. That means the total energy you have used up. Okay, so here efficiency just equals to the useful energy output and over the total energy input. Okay, and also you can use the formula that the energy over time taken. like the work done over time taken just equals to power. So once you over the T at the top and the bottom, it can transfer into the useful power output and useful power, or oh, sorry, use total power, okay? Total power, okay? So here is for the efficiency part, okay? So in this lesson, we have learned about how we can calculate the efficiency, power, and energy, and hope you can just fill in all the questions after the classes, okay? So here's our today's lesson. See you next time. Bye.